Hi, my name is Trina, and today we're gonna talk about normal strain. Strain, represented by the Greek letter epsilon, is a term used to measure the deformation or extension of a body that is subjected to a force or set of forces. The strain of a body is generally defined as the change in length divided by the initial length, or it can be denoted as E equals delta L over L, where delta L is the change in length and L is the initial length. Often, the change in length of the bar delta L is simply referred to as the total displacement, or gamma. In that case, strain can also be denoted as E equals gamma over L, where gamma is the total displacement and L is still the initial length. The elongation of the bar is assumed normal or perpendicular to the cross-section. Therefore, like stress, strain is called normal strain. Similar to stress, a tensile strain is generally considered positive, and a compressive strain is considered negative.
Hi, I'm Japsa and I will be discussing stress-strain relationships. So here we have the stress-strain diagram of a mid steel. So notice that here in the graph, there is a split of the true fracture stress and a fracture stress. So in the fracture stress, the area throughout the entire graph is actually the same. Where in the true fracture stress, the area changes starting from the strain hardening to necking. This is actually due to the necking where the area changes in real life application. So the relationship of the two, stress and strain, is actually modulus of elasticity. It is the slope of the strain versus strain, the stress versus strain diagram, where here is the derivation, where E is equal to sigma over epsilon, where E is the modulus of elasticity, sigma is the stress, and epsilon is the strain. So further, we can derive this formula, which is P over A over delta over L, where P is the force, A is the cross-sectional area, delta is the deformation, and L is the residual length of the material. So we can manipulate the equation to obtain the deformation formula, which is PL over AE. That is all.
We are to solve a simple strain problem. A bar of varying section is loaded as shown in figure 2. Determine the total elongation if the modulus of elasticity is equal to 2 times 10 to the 5 Newton per millimeter squared. There are 3 sections in the bar with its applied load and length. For section 1, the area is equal to 40 times 40 is equal to 1,600 millimeters squared. There is an applied load on the left side, which is 120 kilonewton, and on the right side there is 3 loads applied. 120 plus 220 plus 116 minus 260 is equal to 120 kilonewton. Therefore, the end of deflection is equal to PL over A, which P stands for the applied loads, the length, and A is the cross-sectional area of the bar, E is the modulus of elasticity, which is equal to 0.28 millimeters. For section 2, the area is 25 times 25 is equal to 625 millimeters squared. There are 2 loads on each side of the section, which is 220 minus 120 equal to 260 minus 160 equal to 100 kilonewton. So the end of deflection will be equal to 0.8 millimeter when you substitute the values to the formula. For section 3, The area this time is 30 times 30 is equal to 300 millimeters squared. There is there are three loads applied on the left side and one load on the right side. Equating, we will get 160 kilonewton. And for the end of the platform, PL over AE is equal to 1.0667 millimeters. Therefore, the total elongation is the sum of the individual elongation for compression. End of the platform for the first section, second section, third section is equal to 0.548 millimeters.
Good evening. I'm here to talk about strain problems on strengths of material. So, a steel wire of 30 feet long hangs vertically and supports a load of 50 pounds. Neglecting the weight of the wire, we are tasked to determine the required diameter if the stress is not to exceed 20 ksi and the total elongation is not to exceed 20 inches, assuming that our value for E is 29 times 10 to the 6 psi. So, how do you solve this kind of problem? Initially, we know that we have formulas that we discussed during our theory section. So, we remember that based on the maximum allowable stress, we can obtain that P over A, which should give us 500 over 1/4 pi d squared is equal to 20,000. Algebraically solving for the value of d, our diameter, we would obtain a value of 0.1784 inches. But this is not yet our final answer. We can still check if it will hold true, because we have another formula that we can apply using PL over AE, which is based on the maximum allowable deformation. Given that now, let's try to solve this again algebraically, in which you can also input in our scientific calculator by shift solve. This would give us a value of diameter of 0.1988 inches. So, we have to choose which is our final answer. But remember that our limitation is 20 ksi, or that the elongation is also not to exceed 0.20 inches. So, we will pick the value that is higher. So, this is our final answer. Thank you very much for listening to this lecture video.
So in this example, an aluminum bar having a cross-sectional area of 160 millimeters carries the actual loads at the positions shown in the figure. If E is equal to 70 GPa, compute the total deformation of the bar. Assume that the bar is suitably raised to prevent pop. So the formula we use for the deformation is PL over AE. In the first bar on the left side, Y1 is equal to 35,000 times 800 all over 160 times 70 times 10 raised to 3. So the total deformation of the first bar, the 0.8 meter bar, is 2.5 millimeters. For the second bar, the middle, We use y2 is equal to 20,000 times 1,000 all over 160 times 7 raised to 3. So the deformation is equal to 1.786 millimeters. Similarly, for the third one, we use y3 is equal to 10,000 times 600 all over 160 times 70 raised to times 10 raised to 3. And we get y3 is equal to 0.536 millimeters. So the total deformation of the bar is addition of all the deformations, with y3 subtracted because it's compression, and while the other two is tension. So y, the total deformation, is equal to 2.5 millimeters plus 1.786 millimeters minus 0.536 millimeters. And the total is 3.75 millimeters, which is an elongation, meaning the deformation leads the bar to elongate to lengthen. Thank you.
Today, we will be talking about statically indeterminate sections. When the reactive forces or the internal resisting forces over a cross-section exceed the number of independent equations of equilibrium, the structure is called statically indeterminate. These cases require the use of additional relations that depend on the elastic deformations in the members. Just like simple strain, these formulas are used in statically indeterminate sections. The unit of deformation is equal to the deformation all over the length. Another formula used is the modulus of elasticity. Modulus of elasticity is equal to the stress all over the unit of deformation. Modulus of elasticity is also equal to the quotient of load all over the cross-sectional area all over to the deformation divided by the length. Summarizing the formula, modulus of elasticity is equal to the load multiplied to the length all over the deformation multiplied to the cross-sectional area. Summarizing the formula or alterating the formula, it will become deformation is equal to the load multiplied to the length all over the cross-sectional area multiplied to the modulus of elasticity. That's all. Thank you.
A theory regarding the statically indeterminate bodies is the three-moment theorem. A continuous beam is one that rests on more than two supports. The continuous two-span beam shown in the adjacent diagram is subject to a partial uniform load as well as several concentrated forces. In this equation, MA, MB, and MC designate bending moments at the supports A, B, and C respectively. L1 and L2 denote the span lengths, and A1, A2 represent the areas of the moment diagrams drawn in the temporary assumption that each of the spans of the beam is simply supported. And A1, B2 designate the distances of the centroids of each of these moment diagrams from A and C respectively. The theorem is in this form is applicable to all continuous beams having all supports at the same level.
Here is a problem about statically indeterminate bodies. A steel bar 15 mm in diameter and 2 meters long is surrounded by a shell of cast iron 5 mm thick. Compute the load that will compress the combined bar a total of 0.8 mm in the length of 2 meters. For steel, E is equal to 200 GPa, and for cast iron, E is equal to 500 GPa. For the solution, deformation is equal to PL over AE. That is load times the length all over area times the modulus of elasticity. Deformation of cast iron is equal to deformation of steel
which is equal to 0.8 millimeters. To get the load of cast iron, use the deformation formula. Deformation of cast iron, which is equal to 0.8 millimeters, is equal to the load of cast iron times 2,000 millimeters all over the area of cast iron, which is pi d squared over 4, and the diameter is equal to the outer diameter minus the inner diameter. That is pi times 60 squared minus 50 squared all over 4 times 100,000 MPa. So the load of cast iron is 11,005 newtons. For the load of steel, use again the formula of deformation. Deformation of steel, which is 0.8 millimeters, is equal to the load of steel times 2,000 millimeters all over the area of the steel, which is pi d squared over 4. D is equal to 50. D is equal to 50. So pi times 50 squared over 4 times 200,000 MPa. So that is 50,000 pi newtons for the load of steel. Getting the summation of the vertical forces, total load is equal to the load of cast iron plus the load of steel. That is 11,000 pi plus 50,000 pi. The total load is 61,000 pi newtons. Converting it to kilonewtons, the total load is 191.64 kilonewtons.
For our second problem, the rigid platform in the figure has negligible mass and rests on two steel bars, each 250 millimeters long. The center bar is aluminum and 249.90 millimeters long. Compute the stress in the aluminum bar after the center load of 400 kilonewtons has been applied. For each steel bar, the area is 1,200 square millimeters and a modulus of elasticity of 200 gigapascal. For the aluminum bar, the area is 2,400 square millimeters and a modulus of elasticity of 70 gigapascal. Based from the problem that was given earlier, it is said that the length of the steel 1 and steel 2 is equal to 250 millimeters. The length of the aluminum is 249.90 millimeters. The rigid platform is subjected to a force of 400 kilonewtons, and the cross-sectional area of the two steel bars is 1,200 square millimeters, with a modulus of elasticity of 200 gigapascal. The cross-sectional area of the aluminum is 2,400 square millimeters, with a modulus of elasticity of 70 gigapascal. For our solution, we would equate the deformation of the steel to the deformation of the aluminum, but would add a 0.10 value, which is the distance between the rigid platform and the aluminum bar. Then, the deformation formula is PL over AE, and the stress formula is the force over area. If these two equations were to be combined, we would form a formula of stress times length all over its modulus of elasticity, and that would be equal to its deformation. We would substitute that equation to the deformation formula, which is this equation, and since there are given values for length and modulus of elasticity, we would substitute it to form this equation of the stress of the steel in terms of the stress of the aluminum. Then, we would equate the forces along the vertical axis or the y-axis to form our second equation. As you can see, the force of the steel bars are multiplied to 2 because there are two steel bars acting on the rigid platform. It was then added to the force of the aluminum bar to the rigid body and the force acting upon it, which is the 400 kilonewtons, and converted to newtons. Then we would form this equation, which is 2 times the force of the steel plus the force of the aluminum is equal to 400,000. Since the equation of the stress is force over area, we can derive it to the equation of the force, which would be equal to the stress times the cross-sectional area of it. Then we have a equation for the stress of the steel, which is this equation, and we would substitute it to this equation so that we can get the stress of the aluminum, which is 22.48 megapascal. That answers the question to the problem.
Statically indeterminate bodies. Problem. The rigid platform in figure P-1 has negligible mass and rests on two steel bars, each 250 millimeters long. The center bar is aluminum and 249.90 millimeters long. Compute the stress in the aluminum bar after the center load P of 400 kilonewtons has been applied. For each steel bar, the area is 1,200 millimeters squared and modulus elasticity of 200 gigapascal. For the aluminum bar, the area is 2,400 millimeters squared and modulus of elasticity of 70 gigapascal. Part of the solution for this problem would be the actual deformation of each bars. As we can see, the length of the steel bars is not equal to the length of the aluminum bar. They have a length difference of 0.10. Thus, that difference would affect the actual deformation of our bars. For this case, the actual deformation for the steel is equal to the actual deformation of aluminum plus 0.10. Actual deformation is also equal to the stress times the length over the modulus of elasticity. Transforming our first equation to the equation of actual deformation, we will be having the stress of the steel times the length of the steel over the modulus of elasticity of the steel is equal to the stress of the aluminum times the length of the aluminum all over the modulus of elasticity of the aluminum plus 0.10. Then we substitute the values of the given from the problem. We have 250, 200,000, 249.90, and 70,000. After substitution, we will have an equation which is 0.00125 times the stress of the steel is equal to 0.00357 times the stress of the aluminum plus 0.10. Simplifying this equation, we will have an equation of the actual stress of the steel in terms of actual stress of aluminum, which is stress of steel equals 2.856 times stress of aluminum plus 80. The solution for this problem would be the summation of forces along the y-axis. Observe, there are 3 upward forces and 1 downward forces. This will give us an equation of 2 force of steel plus force of aluminum equals 400,000. Stress has an equation of force over area. We can use this force over area and substitute the equation for the force, which is stress times area. Substituting this formula, we will have 2 times stress times the area plus stress of the aluminum area equals 400,000. We'll substitute again from the given of the problem and from the equation we got from the first part of the solution, which is actual stress of the steel. We will have 2 times the quantity of 2.856 times stress of aluminum plus 80 times 1,200 plus stress of aluminum times 2,400 equals 400,000. Then we will have an equation which is 9,254.4 times stress of aluminum plus 192,000 equals 400,000. This equation will give us the value for the stress of aluminum, which is 22.48 megapascal, which solves our problem.